Now, Poisson random networks go by many different names. Okay. Let me just close this off because this is being truculent. And I'm just going to close this previous model that we had built. It's not really serving much function. Okay, so we're going to go up to environment now. And we're going to now, environment. And we're going to go change this from a ring lattice to what's called a random network. And I'd like you to change the layout type. Well, heck, let's keep it as ring. Let's see what happens. I mean, it'll probably endeavor to do something. Okay, so a random network is kind of the polar opposite in a way of a ring lattice network. Ring lattice only connects people who are logically next to each other. In a Poisson random network, any two pairs of nodes have the same chance of being connected. So it's just for every possible pairing of nodes, it's just going to be flipping a possibly weighted coin. So biased coin, maybe it's 0.2 or maybe it's 10% chance or 1% chance, and connecting them if it turns out heads, right? And not connecting them otherwise. So it has no preference at all for any sort of spatial or topological locality. There's no greater likelihood that that I'm connected to the friend of one of my friends. In other words, there's no more overlaps in the connections of two neighbors than among two arbitrary nodes in the population. Typically, our connections in the real world have a lot of locality. Okay, it's not a ring lattice type extreme locality, but people. If I know someone, if I know two people, if I know A and B, chance is pretty good that chance is better than average for two people in the world that A knows B too, right? Because those two people might be drawn from an office, or they might be drawn from my field of study, or they might be drawn from my family, or whatever. And there's a pretty good chance, higher than average chance they know each other, okay? So there's actually a lot of locality in the networks you see in the world. Physical locality reflecting where we live, logical locality reflecting the different network context, family, office, social groups, etc. And so you get a lot of sort of so-called triangles, cases where, again, I know A, I know B, and A and B know each other as well. Okay, that is not observed at all within a Poisson random network. It's just has equal chance. Now, Poisson random, I should note, goes by many different names. It's called random network. It's also called a Bernoulli network, and Erdos random network is another name for it, after a famous mathematician. I think the first one to examine this. So if we have random chosen as the network type, now we have a specification of a mean number of connections per agent there. Excuse me. Sorry, if you change it to? You're saying with the ring lattice, you're saying? Yeah. Okay, so you folks don't have to follow along, but that's a great question from Sergey. So we're flipping back for a moment to ring lattice to see how connectivity would differ. So I'm still going to display it with a ring layout, but let's think about this a bit. So what we had already was 2. So what that means is we're all lined up, right, in this long line, and I'm connected with person on my left and person on my right. That's what it means. 4 would mean, if I did 4, it would mean I'm connected with 2 people on my left and 2 people on my right, 2 adjacent people. Okay. So let's do 4. Incidentally, I don't remember what 3 does. I'm not quite sure how it deals with that asymmetry and so on. But this is 4, and you actually can't visually see much of a difference. But here, things can go faster because it can kind of hop over someone, right? And roughly speaking, I expect it to kind of infect the whole network in about half the time, twice as fast, right? Because it can kind of jump twice as quickly, right? And indeed, you see it sort of converging there more quickly. Okay, so so great question. I'll leave it as an exercise to examine the impact of odd numbers. Okay, so let's go back to random, and this allows us to specify a certain number of average connections per agent. So how many connections on average do you want some agents to have? That doesn't mean they all have that number. Some may have more, some may have less. Okay, some may have more, some may have fewer.
So that becomes an average from the strip and ring lattice.
Yeah. So here it's an average. For ring lattice, it's actually an integral number, I think. So in other words, it's 0, 1, 2, 3, 4, 5, 6. Here it's actually a mean. So let's go run this with 4, right? So if people on average have 4 connections, and I left it as a ring. This is a ring layout of a random network, right? You can argue about the aesthetics of it, but it's actually one way of kind of trying to visualize a quite complicated connectivity pattern. Now, I'm going to start running that again. So here the infection is seeded, and compare the speed of that spread to the speed with ring lattice. It shoots up very quickly compared to ring lattice, very quickly. Because this contains gobs of global connections. I mean, there's really no notion of locality. Again, there's no notion of kind of a little group of neighbors in any meaningful sense, because again, my friend and I have basically no relationship in terms of our other connections. No sort of regularities in terms of our other connections. So here it rises very quickly. We have a lot of connections, in other words, which span this space, right?
Is that a knowledge on Facebook?
Sorry?
Is that the spread of knowledge on Facebook?
I would argue that Facebook probably has a lot of locality associated with it, but there are some long-distance connections. And in just a minute, we'll see how we can merge the two, okay? But let me just visually contrast these two again. So visually, I'm going to be going back and running these with a ring lattice. And you'll notice what's clear here is that the middle is a big gaping hole, right? There's nothing in the middle of that bagel or donut. There ain't nothing there.
There's no space. You can't like move through it. You can't have a network. You have to go along.
You have to go along that sort of edge here to communicate the infection, right?
So the distance space in the ring lattice,
Yeah.
if you went 50, it would have to be 50 units around the ring as opposed to 50 units
Yeah.
through the ring.
That's exactly right. Compared to distance space where you can spread in 2D in different directions. So there, that was for ring lattice. For the random network, Poisson random, we have that whole middle area. We have some connections around the periphery, don't get me wrong. There's some connections that, just someone who happens to be laid out next to you. But there's really no principled reason why some person has to be laid out next to another. I mean, I believe what is going on behind the scenes is it's just putting arbitrary people next to each other. Because there's no rhyme or reason why it would get two other people. I mean, you could try to look for patterns, but they'd be artificial. They'd be just statistical aberrations. So really, these are sort of have arbitrary ordering along the periphery, and there's some connections along there. Not here, for example, but here you can see some connections. But there's a ton that go across, and those things that go across make the world of difference when it comes to rapid propagation of the infection, because those are the shortcuts it takes. Those are the ways in which it hops from, oh, look at that. Just when I needed, okay, what happened there? It relates to what Chris was saying a couple times ago. What happened there? They just ran it. Where's the infection?
There was one person who got the initial seed wasn't connected to anyone.
So that's a possibility. In any case, there was a red, but they recovered.
Oh, okay. They just blink?
They just blinked. I saw them blink. I didn't blink. They did. And that blink was short-lived enough that probably because of some aspect of their connectivity. I mean, I guess they probably had some connections, but it wasn't enough, evidently, in this particular case, given the rolls of the dice, to get anyone infected. So again, this is a warning about the stochastics here. You know, there's a lot of random fluctuations here, and sometimes those are more pronounced than others. This is a case, which I'd guess is very unlikely for this particular one, but it's possible, where, you know, the network's dynamics, the average time to recover and so on, and the number of connections per node is such that a reasonable fraction of the time you get no spread. Okay, now this person here, okay, now it jumped over, and you'll notice that spread very quickly globally, right across the pond from them.
It's kind of slow in the beginning, but then it starts accelerating.
Then it starts accelerating, that's right. So here, I want to distinguish that it is spreading globally, but there's no, people here do have variability in terms of their connections. What I'm going to do is, I'm going to go create another, a little experiment, which is going to have, you know, tiny population or something like that. And I'm going to set it up such that we have, okay, we're all set for that. Parameters, remember, that's how I set the parameters. I'm going to set it up so that we have a very modest number of connections. Let's say 10, okay? So remember what I just did there is I went and I right-clicked on network, minimal network thing. I did new experiment, and I went through that and just told it the default settings, just named it something different. And then within this, I went to parameters and set the parameter for it, the sole parameter. Why does it only give one parameter? Where's that parameter coming from? Anyone remind me? Yeah, it's from main. That's a parameter in main. That's the parameters, again, are the conduits of communication from where you create the thing to that thing you're creating to tell it what to assume. We saw that with the population creating the agents, telling them what to assume as far as heterogeneity for income. Here, this is the thing that's responsible for creating main, and we can tell main what to assume for the population size. And we can do that by virtue of the fact, ladies and gentlemen, we can do that by the fact that we only have one parameter here, population size.
And if we
Right.
omit it here, we have the default in main.
That's if we omit it here, we have the default in main. That would okay. So I think this is actually filled in textually with the default. So in other words, the default specifies the value when you create a new simulation. What is it going to fill in here? Okay, okay. So I think actually you would need to. I don't think it had actually run without. I may be wrong. Maybe it does do the default. Oh, yep, yeah, it does the default. Okay, so I misspeak. It actually does copy that as the default. Oh, look, it filled it in again. So yeah, it apparently just uses the sort of default to fill it in if you're not so generous to do it yourself. Okay, so I'm running this, and I'm doing this in hopes that we'll get a kind of clearer view. Okay. So this lends a sort of a clear view to things. Now, do all these nodes have an equal number of connections? No, they certainly don't. So for example, this individual has 5 connections, right? And this individual here has 6 connections. This individual up here also has 6. This individual here seems to have 8 connections. So there's some variability in connections here.
Even if you say connections per agent is 3 or 4.
Right, and that's what we actually, well, to be clear, I'm talking about if in the network properties we had set, so network properties, we set connections per agent to be 4. That's the mean. It's trying to get that for the mean and sort of figuring out what the network density is. Okay, so 4 connections per agent. How many networks are there in the population? Then what must the probability be that a given pair is connected? That's what's going on logically right now. Now, this is not going to be exactly the mean that it's going to get for the. If you look at the mean across the network, it's not going to get this exactly. It's going to be a little bit off, but that determines the probability 2 people are connected. Okay. so the distribution is going to be for a given person, you're going to have a Bernoulli distribution actually for a given possible connection, and so the whole thing is going to be binomially distributed for a person. There's going to be some number of connections. I've got to think about that a little bit, but definitely each connection is Bernoulli, and for a given person, you're going to have a set of possible connections to whom, and so yes, it's going to be binomially distributed with a certain probability, and they're going to have, if you have that person, n people in the populations, you're considering a given person, they're going to have n minus 1 possible connections, and for each of those, there's just some chance that it's going to be connected. Note that connection here is bidirectional. So if A is connected to B, B is connected to A. Okay? There are ways, so that is true in AnyLogic. There are ways to mark a connection manually as to which way it goes and have it observe that semantics. But be aware that connections by their sort of by default are bidirectional in AnyLogic.
Sorry,
Okay.
I
Yeah.
think I must have missed something simple, but
Sure.
if the connection per agent on average is 4 just now,
Yeah.
when we see the
Yeah.
chart, each one has at least 5, right?
No, that's a good question. Okay, let's go check it out. Let's go check it out. You may be right. I think you're right. The ones I noted at least had 5. So that should be the mean it's shooting for. So here we have, well, okay, so here's a 4, right? And here's a many more than 4. 5, here's a, okay, that's the 4. Yeah, you're right. It's actually, no, but like this one is not connected with there, right? This one is not connected with this one and so on. Yeah, it does dictate the probability of connection, this thing, but you're right that it is biased in an interesting way here. And it'd be interesting to study that. I mean, there is one case in AnyLogic where I know you specify that, and it actually turns out to be twice that.
Maybe it's because there's only 10, so
Because the small number issues, small sample size issues, and it's biased in one direction. That could be. It'd be an interesting thing to kind of play around with it. Extra credit.
Did you track that by like,
Yeah.
like say you wanted to know that,
Yeah.
create a variable,
Yeah.
just averages it,
Yeah.
do like a trace line or something like
Yeah.
that? And
We'll see how to do that. In fact, I'm tempted to throw caution to the wind and just do it right now, but we may do that later today. Okay. If we don't do it today, we'll do it next time. Okay. Whereby we can do it. Yep, we could very easily check what the actual empirical, mean is. Okay, so we've just seen this, and as we increase the sample size, or the sample size, the population size, we'll probably have a closer convergence, is my guess. I think that's true. Let's try connections per agent 1. Let's just see what. Let's say 0.5, right? Sorry. Let's see if it first of all if it coughs. Yeah. So here we do have a lot with 0, some with 1, and I'd say we have 6 of them with 1 and 4 with 0. So it's not exactly 0.5, 0.6, but correct. Well, okay. It's actually quite straightforward. So if you think about it, if we have a network with n agents in it, right? There's only a certain number of possible connections, right? And you have to think about the mathematics a little bit carefully because connections are by nature bidirectional. So if A is connected to B, B is connected with A. When we have three possible agents, we only have 3 possible connections. And in general, I think if we have n agents, we're going to have n times n minus 1. So each person can only be connected to n minus 1 other possible people divided by 2. Does that, so this would be 3 times 2 divided by 2, which would be 3 possible connections here, for example. And this is the number of candidate connection, sort of, because A, to put it another way, A connected to B is the same as B connected to A. So we have that factor divided by 2. So that's the number of candidate connections which you have to choose among, right? And for each of them, you have a certain fixed probability that it turns out to be true, right? If we have a mean connection per agent, call it C, okay? And we have n individuals in the population, then that yields sort of, we are seeking a mean of n times C connections for the whole network, right? And if we want that many connections out of this many possible connections, the probability of a possible, so all it's doing is basically figuring out for every pair of connections, logical pair, A to B, same as B to A, there's a certain probability that it's in fact realized, a certain probability that it's in fact true. So for any given connection in that network, we have n times C divided by n times n minus 1. So these are the set of all possible connections, the number of possible logical connections, and this is the number of ones we want, right? We want these. And so the probability that a given connection will in fact be realized is P, is 1 divided by the other. Does that make sense?
Yes, I'm wondering this n times C, maybe it's 2n times C?
Yeah, okay.
But it's also the direction.
It's bidirectional.
It's bidirectional, right. So this may be, okay, yeah, so I'd have to think about that. It may be 2 times this, that's right. You'd have to think of that, cancels out in the way. But yeah, I think just like that, we're off by a factor of 2 potentially. So that's how it figures it out. Quite straightforward. And it doesn't guarantee that you're going to have exactly that many. It'll be on average you have 2 NC or NC number of connections, but there's a distribution around it. In fact, that's a Bernoulli distribution, right? Binomial distribution, excuse me, around it. Okay, so what we've just seen is situation where we have random connections between agents. Here, there's just no regard for locality in any sense of the word. There's no regard for sort of network substructure or anything. We just have these agents that are more or less randomly connected with anyone else in the world. Now,